if you're joining this seminar thinking you're going to hear about probabilistic inference in neural circuits, you're going to be very much disappointed. I basically had a new batch of students joining the lab the last 4 or 5 years, and they hadn't really bothered reading what I was doing before, so none of them joined the lab with the idea of doing probabilistic inference. That was very good timing because I was kind of getting a little bored with the probabilistic stuff. We've been doing that for 20 plus years. And so they basically dragged me in completely different directions. And so you're going to see that in the talk today. I'm going to talk about two projects that have to do with compositionality at completely different levels. We'll see how I'm doing with timing. I don't know how much time I have with this for the second one. First thing I should mention is feel free to interrupt me as I go along. In fact, I much prefer that. If I feel like the question that would be better for the end, I will tell you. But really don't hesitate to interrupt me, particularly if you're lost on details. The project you're going to hear about, they're not published, and I've presented once or twice at most. So I know from experience that I screw up on many slides when it's in the early stage of presenting a talk. So, all right, so the first project is what the title is really referring to, and it's a project that has to do with indeed compositionality that you gain from using language. And while I'm presenting the work that you're going to hear about is really the work of a grad student lab writer, Rivland. Even though many of you are machine learning people, you probably know that when you train an animal on a task, it usually takes thousands of trials to teach those guys the simplest 2SC binary choice like task. And interestingly, whether you do that with rats or with monkeys that have the brain that are 100 times bigger, it still takes thousands of trials to get them to produce or to perform well on very simple tasks. And in case you don't know, I think all of you know from first experience, we have the same issue when we train artificial systems, right? This is a bad slide from the famous DeepMind work on Atari game, where they show performance as a function of number of epochs. In fact, if you read, you go like, oh, 200 epochs, not so bad, until you read the fine print and you realize that what they're talking about is 200 million epochs. So absolutely enormous number of trials. So all of this stands in really stark contrast with what we see every day in psychophysics labs all across the world, which is that you can bring a subject in a lab, place them in front of a monitor, and then tell them something like, respond in the direction of the stimulus presented with greater strength, and off they go. And if the task is simple enough, they will perform well the very first time they perform the task. Right, so no need for thousands and thousands of trials for those people to learn the task. You just tell them what to do, and right away the network is somehow rewired dynamically so that now you perform the proper sensorimotor transformation. And that's really something that personally has really fascinated me ever since I've joined neuroscience, which was a few years back. Salk Institute, indeed, when I was grad students. But before that, actually, I was in Paris. And I heard the very first scientific talk I heard was from Jerry Fodor. And the talk was entitled, Why is Connectionism a Bad Idea? Classic Jerry Fodor takedown on neural network. So you have to realize we're in 1987, that's embarrassed to say. 2 years earlier, the latest version, the backprop algorithm, had been published by Yann Lequin on the one hand and Jeff Finton on the other hand. And we're all going crazy. In fact, 87 looked very much like 2020 in the sense that all of us in neuroscience were training neural networks to make them because they looked like the brain. And we thought that would be the way to study the brain. 30 years later, we're back at doing these kind of things. In any case, what Jerry Fodor was trying to point out is something that Gary Marcus is saying every chance you get, which is that neural networks are just not the right architecture to model things like language that need symbols and compositionality. And at the time, again, we're in 87. I must say, I was listening to this, I was like, this guy is making some really good points. And in fact, I started reading the work of Jeff Ellman and other people at the time were doing language. And I was not particularly impressed by what those systems could do. It was really, really elementary and very far cry from what we would call language. But this was all in '87. A few years back, the transformer architecture completely changed the game for natural language processing. You guys, of course, are well aware of this, but the system looks way, way different and way more and way better than they used to be. And so what we wondered with Ryder is whether the time was ripe to try to understand how sensorimotor transformation can be reshaped by linguistic instructions, and whether we could mold that with neural networks, just like it is in the brain. Because for me, when I heard Jerry Fodor, I was like, okay, he makes some good points, but the brain is a neural network. And we think we understand the basic principle of neural networks. So something got to give. How do we get language out of those neural nets? All right, so that's basically the starting point of this project. And to determine whether we can understand how neural networks can take linguistic instructions to perform tasks, we decided to compare two types of architecture. The first architecture we're going to call the simple model. This is based on the paper that was published by Yang et al. In 2019, in which they train an RNN on multiple tasks at the same time. 16, I think it was 14 different tasks at the same time. And they had one of the input layer of the network was specifying the task rule vector, so the task at every trial. This was done by just assigning arbitrary orthogonal vectors to each of the tasks for the input representation here. We're going to compare the performance of this network to another network, which is also going to train on 16 different psychophysical tasks at the same time. But for each of the tasks, instead of being told this is task 1, task 2, the task is going to be described just by a linguistic description of what the task entails. Okay, so a few more details about those architectures. The sensor input for this architecture is made of 3 groups of neurons. The first neuron is meant to be neurons that respond to the presence of a fixation point. So as long as there is a fixation point on the screen, this is on, and then when the fixation points turn off, this unit turns off. Then we have a first sensory layer here, which here you have arbitrary dimension. Think of it as direction, okay? And along the x-axis is time. And so stimuli are represented by hills of activity along this one-dimensional array here. So this is the case here where you have 2 stimuli that appears at these times and are maintained throughout the trials until the extension of the fixation point. And then we have a second modality. So think of it as maybe this is vision and this is addition, when again, this is direction that's being mapped here as a function of time. So in some tasks, only one modality will be presented. In other tasks, 2 modalities might be presented, especially when we're doing multisensory type of decision making. The task rule vector is a multidimensional layer. And again, the state of that layer is determined by the identity of the task. In this case, I'm showing a one-hot vector for this task, but it doesn't have to be a one-hot vector. In fact, in our case, typically it's not one-hot vector. But what's important is that the task vector is maintained on throughout the duration of a trial. And then for the output, the motor output, it's also going to be a motor output in terms of direction. So again, you have direction along this y-axis here, time along the x-axis. Here's the response of the network, which is shown, again, take the form of hill of activity, and take the form of hill of activity because this is how we train the network. The network is trained by showing this pattern here with backprop through times. And you see that in this particular case, this is a decision-making task, and the network has to respond in the direction of the strongest stimulus. So that will be the top stimulus, which is why the target is provided to be a hill on top of this layer here. And you see that after training, this is exactly what the network is doing. The other architecture, the one that has the language module on the side here, is pretty much the identical network with the same sensory input. The big difference is that the last layer of this language module is a layer whose dimensionality I can't remember, like 20, I think it's 20-dimensional layer. And the activation of this layer is a result of processing instruction of the type response in the direction of the stimulus with greater strength. And this is going to be a big transformer network we're going to throw at this, which is going to basically turn that into a language embedding of 20 dimension, which we then maintain throughout the trials, just like we did with the task instructions. As to the output, exactly same deal as before. So I hope everything's clear. If not, again, feel free to interrupt. Okay, for the language modules, what we're going to be using is effectively every time it's going to be the same transformer architecture. The only difference is going to be how we train, or the kind of pre-train architecture that we're using, because in many cases, we're not training ourselves. We're going to take pre-train architecture. The first one we used is GPT-2, which probably most of you have heard about. Why not GPT-3? Well, just because we cannot get the code for GPT-3 right now. I think it's being trained by, I forgot which organization is training it on their own. So soon the code should be available. But for GPT-3, you cannot get access currently to the synaptic weights. So we went for GPT-2. Just as a reminder, GPT-2 is a network that's self-supervised. It's trained on predicting the next word in a sentence, given all the words that preceded that word, right? GPT-2, while being pretty small by today's standards, nonetheless had already some pretty remarkable ability to come up with completion or answers to questions. So here's a case where after it's been extensively trained, the network is given this as a prompt. I'm not going to read it because I think most of you have seen many demonstrations of those. The model completion after a fairly amount of, in this case, there's a lot of cherry picking, but eventually GPT-2 comes up with something that's just absolutely remarkable in terms of like its proper English with proper syntax, and even better, proper semantic, given the prompt that it was given. So for us, when we saw that, we thought, look, yeah, we could get into the argument about whether those networks really truly do language and have notion of semantic. Frankly, I got bored with those discussions. When I saw that, perhaps because I'm old and I've seen how crappy the language models were in the past, I was like, okay, this stuff, I don't know, call it whatever you want, but it seems to have some notion of semantic. Look, I asked this question, it comes with this response. That's pretty darn good response. And so I figured maybe this level of semantic will be enough to instruct another network to do something. And that's what we're testing with Rider. So what we're going to do here is use a variety of tasks. As I mentioned, there's 16 of them. I'm not going to go through all of them, but I'm going to give you a few examples. Those are basic, so the same tasks that were used, by the way, by Yang et al. In their 2019 papers. And those are standard psychophysical tasks that are used extensively in the animal literature to train animals. So we thought that would be a good start. And an anti-RT, that's for reaction time, go task is a task in which instruction is response in the opposite direction of stimuli immediately. So here the stimulus appear and the network has to respond in the opposite direction. So the stimulus is presenting lower parts here of the direction axis. And so the response is 180 degrees away. But importantly, for any given task, we don't provide just one way of describing the task. We provide multiple formulation of the same instruction. So in some of the trials, this task might be prompted by when cued, choose the converse direction. In fact, Rider went through the effort of generating for every single task 15 different ways of describing the same task. Believe me, it's not that easy to come up with 15 different ways of describing an entire RT-Go task, but it did it. And the idea is that the network cannot just like lock onto like some keywords or particularly a sequence of words. We wanted to force the network to really extract the meaning of all those different sentences and to understand that they all correspond to exactly the same set of actions. Here's another example of a task. It's a multisensory decision-making task where this time the instruction, one of the instruction can be respond in direction of greater strength average over both modalities. So we have two modalities here. It has to take the average of those in response in the direction that has the best average amplitude. Here is a delay matched to stimuli task, which involves a little bit of memory. It's a bit different. So if the first and second stimuli are in the same direction, then response, otherwise do not respond. So it's also kind of a go, no-go type of task. So here you have two stimuli that appears in a row at the same location. The network responds at that location. Here, there are two stimuli that are at different location, and the network has to hold its response. So again, I have 16 of those organized in 4 different families of tasks. And I think that's all I want to tell you about those tasks and all the details. By the way, all this is on a preprint on bioRxiv. So if you're missing details, you can always go check out. And there you'll find all the details about all those different tasks. So the first thing we did is we trained the RNN with or without a language module on all those tasks. And I can tell you it works just fine. You get to near perfect performance for all the different tasks, whether you have language or not. But that's not so much what we were interested in. This was just a starting point. What we wanted to do is the following test. You train on 14 of the tasks and you hold out 2 of them. And then you test how quickly the network generalizes to the 2 tasks that were being held out, right? What I'm going to show you is basically the results. We're going to, of course, vary the 2 tasks that are being held out. We just pick 2 random tasks every time. And all the results you're going to see are average performance over all possible sets of held out tasks. Okay, so it's not one specific one, it's the average. And the graph you're going to see now is the performance on the held out task as a function of the number of training examples just on those tasks, right? So I've trained on 14, I'm now exposing the network to new task, and this is the number of trial on this new task, and that's performance. First thing to get a baseline is to test the performance of the simple network that doesn't have the language modules. And this is what you get. Note there is a gap here in the middle, which is why the curve here is broken off. First thing to notice, zero shot learning here is at 27%. It's not, so you might wonder, wait a minute, 27%, is that good or bad? Because those are 2 AFC tasks, right? So chance levels should be 50%. So you might think, how come it's not starting at 50%, which would be worst case scenario? That's because of the way we compute performance. We declare that a trial is correct if it's at the right location, but with more or less the right shape. It has to be kind of a Gaussian. It has to be at the right location. It has to have the right timing. And because of that, if you wire a network randomly, you would get 0% correct, or 0.1 or whatever. So really chance here is at 0%. So 20% or 27% here is not so bad. And what it shows us is that there's enough overlap between those tasks. This task is reasonably simple, that just by chance, if for instance, you're exposed to a new task and you continue to perform the old one that you remembered, you might get it partially right. Okay, so this is actually really important because this is giving us the baseline in a way that gives us a chance level. That's just due to the structure, the shared structure across the different tasks. All right, so now instead of using the simple network, we're going to run GPT-2. So we're putting GPT-2 here. And now remember, when we have a new task, the new task is provided along with the verbal instructions describing that brand new task. And the question is, can the network, just based on this verbal description, immediately perform the task at a very high level of performance? And the answer is no. So this was the huge disappointment after literally months of work. I think there's 1 year of work there where we're eagerly waiting to see what GPT was going to do. And to our dismay, we found that it's actually at 27%. Zero-shot learning, just like the network without language. The people who argue that GPT-2 doesn't do language and it's just like a dumb, big memory dump, that sounded like good news. To us, especially to Ryder, this was a pretty sad start to each PhD. Okay, so the network does learn a bit better with a language module, but that's not really what we're after. We're really looking for like really nice generalization here, and we're not getting it. But then we thought, okay, maybe GPT-2 needs a little bit of fine tuning to really understand the meaning of the new task. So during training, instead of just taking off-the-shelf GPT-2, we allow the error gradient to backprop into the into the last 2 layers GPT-2. So we don't want to retrain everything, but we thought maybe a little bit of fine tuning with GPT will do the trick. And yeah, we did get an improvement. We got 2.45 zero-shot learning, but it wasn't particularly impressive, right? And the learning is just about as fast as without training. So just to be, yes, go ahead.
Interrupt this question. Oh, what's your interpretation of why it's learning faster than? Because so if GPT-2 is just doing classification of your inputs, it should be the same as the direct instruction, right?
Yes, exactly. So I must say the fact that it learned faster made it think that there is more to it than just a classifier in GPT-2. We didn't investigate really where it comes from. We didn't run any kind of experiments or anything. So I cannot quite answer your questions, but what is true, the fact that we saw better learning is one of the things that encouraged us to keep going, because we thought it wasn't like GPT-2 was not helping at all. And that's actually why we did the fine tuning, and it got a bit better, but I can tell you we were still very much dismayed by this. In fact, for quite a while.
Maybe a related question.
Yes, go ahead.
So if I understand correctly, what you expect from GPT is to capitalize on the compositional nature of the linguistic descriptions.
Yes.
So why did not happen at all? So do you have some intuition of that? So maybe, so one thing I thought of is that if you used something even simpler like word to back on the sentences, that would still give you a metric that didn't exist in the orthogonal task description vectors. So that should already give you like some advantage over the orthogonal ones. So
can we get back to this after I show you the summary? Because I don't have word to vec. I know it doesn't work. We've tried it. I won't show you, but I'll show you at least bag of word, and you'll see that it does something, but it's nowhere near what we're gonna eventually achieve with networks. Because GPT-2 didn't work, but the reason I'm talking to you is because eventually we found architecture that worked, and it's not so much architecture, they're all transformers, but we found training regime that worked. So with BERT, it's another one of those language things where there are two differences. The first one, we don't think it matters, but we haven't tested that very thoroughly. But the first one is that the network is not trained to predict the next word in the sentence. It's instead trying to predict a word given the word that preceded it and the one that followed it. Okay, so slightly different with GPT-2, but here's where we think really makes a big difference. The network is also trained on sentence level comprehension. It's basically given two sentences from a corpus of text, and it's being asked, are those sentences following each other in the text, or are they completely different locations? The idea being that here, this is trying to force BERT to have some kind of sense of semantic that go beyond one sentence. And so we did this, we plugged in BERT in there, and first time we tried it, it wasn't that much better. Turned out that we're still getting pretty bad zero-shot regionalization. But when we start doing the error gradient, we realized that then performance started really jumping to something way better. So we're not that far off. And suddenly we're at 68% zero-shot learning. And with just a little bit of training, we're now at 86% three-shot learning. Okay, so that was encouraging. And that's when Ryder realized there's yet another version of BERT that we could have used, sentence BERT, or SBERT for short, which is trained on the same thing as BERT. In addition, it's also trained on the Stanford Natural Language Inference task. So this is a task in which the network is given two statements, a premise, like the man inspects his uniform, followed by a hypothesis, the man is sleeping, and it has to perform a three-way categorization. It has to say between whether the relationship between the statements is an entailment, a contradiction, or neutral. Right? So in this case, the man inspects his uniform is contradictory with the man is sleeping. So the network would have to say it's a contradiction. So the network's trained on those. You should realize that, the first training, the one on the words, is done on millions, if not billions of words. This is done on a pretty small database of people who generated those statements, right? So it's a bit of a fine tuning on top of SBERT. Nonetheless, that was dramatically better. So if you take off-the-shelf SBERT, no extra training, you do as well as BERT that has been fine-tuned for our particular task. So you get immediately this 68% zero-shot learning. And of course, if you now fine-tune expert slightly, then you start getting even better results. We're now at 80% zero-shot learning with 90% three-shot learning. In fact, those results are about 4 months old. I was hoping to show you the latest one, but the entire simulation is now going on the local cluster. We have the preliminary result, but we don't have the final one. But just to give you an idea, we're now doing 89% correct, and not just on 16 tasks. We're now moved on to 36 different tasks. Some of them, they're really probabilistic reasoning. So somehow I'm back into probabilistic inference, where the network has to estimate its level of confidence and decide whether to respond according to its level of confidence. And that's also, we withhold 4 tasks. And the 4 tasks can be part of the same family of tasks or across tasks. It works better if the held out tasks are from different families of tasks, but even if they're in the same family, we get generalization. Yes, so that's where we are. Oh, I promised back a word, but it's not on this slide. Sorry, we'll have it later on. Yes.
Can I ask again? Sorry. So have you tried pushing it? Like, how much can you withhold? Can you like remove 30 tasks and predict them?
No, so we're pushing at 4 right now. Those are pretty enormous simulations, and we're not DeepMind. That's part of the problem, or OpenAI, right? So there's just one poor guy in my lab, writer, and a cluster here. And indeed, we live in a strange world where we're competing with Google that's just released its 540 billion parameter language module. Yeah, we can't quite move at that speed. But anyway, that's really the latest, literally from this morning. Okay, so ultimately, we're not competing with Google. This is where it's fortunate for us, because what we want to do is we want to use this to start understanding how in the brain, sensorimotor neurons gets reshaped, or the activity gets reshaped by linguistic instruction, things that we cannot do in animals, but we can do in humans. We can record in humans. There's a little bit of that going on. We could make prediction as to what should happen to the activity of those neurons when you give instructions to the people. So I want to really insist on this. I'm not talking here about recording neurons in language area in humans, which is what most most human studies do, because of course the argument is, hey, I'm recording in humans, I might as well study something that's specifically human that I cannot do in animals. But in fact, I would argue there's some interesting things to be learned as well from recording from non-linguistic areas, sensory motor neurons, for instance, in the human brain, and to see how they're influenced by linguistic instructions on the go, on a trial-by-trial basis, something that you would not be able to do in animals. So we played that game in our network. We record from the RNN units, right? Not from the transformer, from the RNN units, and we can plot classic things, tuning curve the neurons, so their sensitivity to directions. Remember, that's what we use in the input, in different tasks. So for instance, for this neurons prefer this directions for go and RT go task. But now, if we look at these neurons for the anti-RT go and the anti-go, so 2 anti-tasks, what we see that the tuning flips to the other direction, 180 degrees away, which makes sense, of course, because it's certainly the motor action has to be reversed, and you see the tuning flips in the other direction. But 2 very important things about this. This happens on a single trial, right? I just give different instructions to the network, and this flips. If on the next trial were to give the instruction for the regular task, it would flip again. Right? So it's not like in monkeys where such flips, you see task-dependent tuning in monkeys prefrontal, but this requires enormous amount of training to see those things flip. So they flip on a trial-by-trial basis. And on top of that, this is a network in which anti-go is held out. So this flip for the sine curve here is actually on a set of instructions that the network had never heard before. Right? So this is really what's unique about what you're seeing here. Now, we can play this game with many other neurons and keep looking at how the tuning curve changes. And what we find is like a whole zoo of responses, some of them that make sense, like this one, others that are much harder to interpret. So of course, at that point, we go with standard dimensionality reduction techniques. You think here, nothing fancy. We're just going to do PCA on the activity in the RNN. And we're going to plot where we are in activity space for different trials of each of the tasks. So each dot here is one particular stimulus configuration, stimulus output configuration. And what you see is a nice organization of neural activity along axes that are make sense with respect to the task, right? So along kind of this left-right axis is really about it's about this anti-direction. So it's really encoding whether the task is what we call pro or anti. Whereas along this direction is a reaction time direction, whether the task is reaction time or not reaction time. And if we go in the simple network, the one that doesn't have language, we see the exact same organization with an anti-axis here and an RT direction axis here. But this is in both cases for networks that have been trained on all the tasks. What's really interesting is what does this kind of organization looks like when you're dealing with a task that was held out. So there we go. Here is now anti-go is held out. It's assigned a dot here. And suddenly you see that the anti-direction that is seen here between RT-go and RT-anti-go does not generalize to anti-go, which had been held out. And that's a big difference, of course, with the BERT network that's been tuned, that even though the network has never seen anti-go, you see that the semantic structure of the task is being preserved in the RNN activity. And this is, by the way, the RNN activity before the stimulus, I forgot, I think it's right after stimulus onset. Yes, it's right after stimulus onset in the RNN. That's what you're seeing here. So we can quantify this using a nice measure that was designed by Bernardi and colleagues in 2020. It's called the cross condition generalization performance, or CCGP. And what do we measure here? So what we're going to look, the way we're going to quantify how well there's generalization is by doing the following thing. We're going to take a pair of tasks, say go, anti-go, and train a linear classifier to distinguish between those two tasks. And then we're going to ask if we use the same linear classifier, but now apply to RT-go and RT-anti-go, no new training, we use the same classifier, how well do we do? And obviously, if there's a lot of structure like this in the representations, then you get immediate generalization to another pro-anti task, but with different features, in this case, reaction time. So here you get a high score, right, for this CCGP measure, and that's the case. So in the case of, if you do that for all the tasks, we do it for all combination of tasks and everything, we find that the CCGP measure is above 0.8 for BERT net tuned. All right, so we can do that now for the simple net. And when you're training on all the tasks, you find also that you get a very high CCGP. And in fact, no matter which architecture you use, you get a high score. Next, you want to do it when there's a task that's being held out. So for instance, when the anti-go has been held out, we know that it's not being placed in the right location in space. And so now you don't get the generalization you were getting. And indeed, your CCGP measure just drops to a near chance, whereas for the BERT net, it continues to work because anti-go, I'm sorry, this is not properly labeled, anti-go should be here. The science dot, even though they've never been seen before, they are in the right location and you get immediate generalization. And in fact, your CCGP measure is going to be high. For all the other architecture.
May I have a question? So maybe I missed it, but so these are all zero-shot generalization scores, right? So that's what you are looking at here.
Zero shot for when you have held out, yes.
Yes. So wouldn't it also be interesting to look at a few-shot generalization? Because even especially if a task is basically flipping another task, you can basically understand the entire structure of the task, except for like the sign of the whole thing. And that means that you almost understand it, but you do have to resolve like one bit of uncertainty. So you will be like pretty bad at zero shot, but very good at few shot.
if all the tasks were that way, I would agree with you, but I'm just showing you anti and pro as one example to illustrate this. Remember, we have 16 tasks and they differ along other dimensions. So we could do it for this one, and presumably it takes indeed a few shots before the system starts getting it. I mean, you saw the learning curve, right? Those are not tasks that requires millions of training cycles. It's maybe a bit ambitious to go back. Yeah, classic problem. But you see that eventually after about 50 training examples, all methods get it, right? But not after less than 10. Like the simple network doesn't, but I don't have the curve here exactly for anti-pro.
Yeah.
And maybe it turns out anti-pro is one that's easier to learn, though that turns out to anti-pro typically is hard to learn.
Yeah, but actually it is the case that when you have the language networks, the derivative of the curve is much higher. So like the few shot, there is a few shot advantage as well.
Yes. Okay, so CCGP measure. Okay, so all right, so what we've done so far is that we've been trying to really model this interaction between language comprehension modules with sensorimotor networks. We've been asking, can we use those language modules to reshape the sensorimotor networks so that they perform the task specified by the instructions? So it's a bit of a modeling of Wernicke's area. So now what we're going to do is the opposite. What we're trying to do is we're going to have a network perform a task, and we'd like the network to describe with words how it solved the task, a bit like Broca's area might do. I think today it's probably not too many linguists among this crowd or cognitive neuroscientists studying language, but I presented this recently to such a group, and they went absolutely berserk on the fact that I would compare that to Broca and Wernicke. There's a lot of discussion in the literature saying that this dichotomy is a bit silly production, but of course my talk is not about what Broca's area and Wernicke's areas are doing. This is just for the purpose of illustration. We studied how comprehension can influence the network, and now we're going to understand how we can do production. So the way we're going to do it is by augmenting our network with a new network that takes as input the RNN activation and is trained to effectively come up with a verbal description or linguistic description of what it is that the RNN is currently doing. And it turns out it's not so hard to learn, because we can train this network at the same time as we train the rest of the network. So what we do is when we train this part of the network here, we present sensory inputs, linguistic instructions, we provide some motor feedback, and we train all of that. And at the same time, we're going to train the other network by training it to reproduce in the output the instruction that was provided in the first place. To which you might say, well, that's a bit silly, because all you're asking is basically to be a parrot that's just going to take those words and repeat those words. But of course, it has to go through this massive bottleneck here of the RNN before it can spit out the words again. So it's actually not that easy for the network even to reproduce its M words. But eventually, the only way that the network can do it is by understanding what is really the semantic of this RNN, or at least to a large extent, that's what we're hoping that the system is going to do. I should really mention that with the transformer here, we're using pre-trained GPT-2 that have been trained with billions of examples, have billions of parameters. Here, this is like in-house little network of a few 100,000 parameters. So it's a baby attempt at this. In fact, we were not too confident this would work. Yes.
Are you, if the output is like something with the same meaning, do you also count it as a success?
You're going to see that in a second.
Okay.
Because in fact, the question is, what is same meaning? Is a very big control. How do you know it's the same meaning, apart from asking humans, which we don't want to do? So I keep hitting the wrong button. So we train on this, but of course, once it's trained, the real test and the fun test is this one. We now, here's what we're doing. We're taking a subject, in this case, a model, we're training it on a bunch of tasks on day one. We send the subject back home. The next day, the subject comes back, and we show them a particular input-output association that corresponds to one of the tasks that the subject has seen the day before. And we like the subject to tell us, okay, describe with word, what is this task about? That's literally what we're going to do here with this network. We're going to train it on 16 tasks, and then we're going to present the network with input, output, so this is what the motor feedback is, for a given task. But we're not going to provide verbal instructions. We're going to ask this network now to tell us with words what is instruction for this task, right? So that's what we're hoping it will do. And the way we do it is we simply backprop the error into the embedding layer, the top embedding layer of my language network here. And we're doing gradient descent on the activity of this layer. So we let in this layer reach a level of activity, which effectively is consistent with the input output for this particular task that we're testing the network on. And once this is stabilized, this is sent to this decoding network that comes up with a linguistic description. Okay, and does it work? Well, here are the kind of instruction that's generated by the network, and don't even bother reading. I mean, we spend hours looking at them and thinking, yeah, it's not so bad. And sometimes there's one word missing, and it's just like, how do we count that? And no, like, well, this is all very subjective. You know how we should do it? We should do it slightly differently. So first of all, we did quantify at least how many times is a network producing the right instruction, that is instructions that were in a training set. So those ones, at least there's nothing subjective about that. And how many times does it like produces other type of instructions? So this is a confusion matrix, right? So this shows you if the attack is go, how many times did the network produce go instructions that were in a training set? And that would be 75%. And there is no confusion with the other ones. Okay. And in addition, we found that 20% of the time, 22% of the time, the network produces instructions we haven't seen before. And the question is going to be, well, are they any good? That's good. Those are new words, just saying things in a different way. But is it really describing a to-go task? And this is the percentage overall of new instruction that we got for the different tasks. And overall, 50% of the time, the network is producing instructions that were not in the training set. But again, are they any good? So how do we test this? The way we're going to test it is by having two networks talk to one another. So we're going to take a network that is shown a particular task, no verbal instructions, and it produces a verbal description of that task. And this verbal description of the task is going to be fed into another network that has been pre-trained on those tasks before, right? And now has to perform the task. And we can see how well does it perform the task based on the instruction that it was given by the other network. And what we found is that we get near perfect performance. In fact, it's very difficult. We need to run the statistical tests, but there is very little difference between the performance of this network when it's based on instruction provided by the other network versus instruction that we provide. Right. So as far as semantic is concerned, those instructions are perfectly valid for this second network. This is true when you train on all the tasks, but interestingly, this also works when the task being described was held out for the second network. So the receiving network has never seen this task. It's shown this task for the first time ever, and it's given instruction from another network. And performance is not as good as for a task on which it's been pre-trained, but it's about the same as what we were getting in the first half of the talk when we're exposing a network to a brand new task. Okay, so the fact that the instructions for the new task are provided by another network doesn't incur much of a cost in terms of performance. You might ask, sorry, go ahead, Sophie.
This is for zero-shot learning, or it's for like fully trained?
So this here is zero-shot.
Oh, okay.
Right. This is a held out task. So this is a task that the second network, the listening network, has never seen. Mm-hmm. It's exposed to it for the first time, and it's trying to perform the task based on instruction from another network.
Okay. Yeah.
Right. Mm-hmm. So I think, and I hope you guys will correct me if I'm not correct, but I think we were the first one to get two networks to cooperate through language. This is literally what we're trying to do here. Some of you might already be wondering, wait a minute, but so far we've trained this network to generate only instruction for tasks it has seen before. We're working on that, and we're starting to have some promising results on network generating instruction for tasks it has never seen before, kind of zero shot again. I'm not showing you this because it's still in the making, but it's actually in the right ballpark. We just need to work a little bit more on that part. Okay, so one question we're wondering about is those networks have similar architecture. In fact, they have identical architecture in the sense that they have the same number of units everywhere in every layer. So instead of using language to communicate between those two, how about just direct neuronal communication? How about copying the instruction embedding that are generated by this network that's trying to describe the task with words and feed it into this other network that's trying to perform the task? That's very much what Neuralink is trying to do, right? This is what Musk is promising us he's going to do, is by connecting your brain and my brain directly with electrodes, and they'll just talk with spikes. Well, when we do this, performance that we get is way worse. It's the gray bars compared to blue, which was the two networks talking to one another. And it's not surprising. Those two networks had the same architecture, but they were trained slightly differently in slightly different ways. And so the weights that go through instruction embedding to the RNN are not the same in both networks. And so as a result, you get this drop in performance. So needless to say, if I were to retrain agent 2, then it will work. But in a sense, that would be defeating the whole purpose of zero-shot generalization, right? So this is actually interesting because it's just like highlights a well-known property of language, is that by virtue of agreeing, all of us agreeing on a common principle and semantic meanings of words, we don't have to retune this when we talk to different people. To a large extent. Of course, anybody who's been in a relationship knows that every relationship means you have to relearn what other people means with words, so it's not perfect, but we get a head start. Okay, so quick words about compositionality. For those of you who are familiar with the Yang et al. Paper from 2019, one of the big claim in the network, in the paper, is that they can do compositionality. So they were training this network with this one hot task encoding in this input layer here. And what they had pointed out is that in their data sets, some tasks, such as anti-Artigo task, is really the combination of Artigo plus anti-Go. Those two together gives you this last task. So they actually showed that indeed the network does the right thing in that respect. If you test the network, if you activate in the input of the network the representation for Artigo and anti-Go, then the network immediately produces, without any training, anti-Artigo behavior. And they go through many examples of that. And very quickly, when you read the paper, you realize, yeah, it works to some extent, not always, as long as the new task being generated is really a linear combination away from the other tasks. As soon as you go nonlinear, things starts breaking down. In fact, even in some cases where it should be linear, it doesn't work very well. And in many cases, I mean, this actually was a source of inspiration with writers. After reading this, we said, look, it's an interesting step toward compositionality. But for compositionality, you really need language. That's what language does, and does extremely well. And that's why we thought, okay, we need to do it with language, with the held out task. And you saw that then the simple network can no longer do generalize with zero shots very well, whereas the language modules can do it with very high level of performance. So that's the language story. Now I'm going to just very quickly tell you about our efforts to try to understand compositionality at a more basic level, because my own intuition with this is that compositionality is a property of neural networks in general, in particular cortex, and it exists to a small extent in animals. And the massive expansion of cortex allowed to get all the way to language. But before that, there probably already is ability of animals to decompose tasks in a compositional way. And with Pablo Tano and other students in the lab, and Peter Dayano, need no introduction to this group. That is its official International Brain Lab picture, in case you're wondering why I'm showing this. So sorry, guys, there's not even the VTA, which is really embarrassing, I think, for Peter, but he picked it. That's his official portrait. So with those two guys, we started thinking about how can you learn in a compositional way in a reinforcement learning context. So just for the sake of illustration, you see that, thank God, we can go beyond the grid world, but we started with a grid world type of example. You have an agent that's trying to get to a goal. And in TD learning, the way that things work is the state of the system is of the agent's position of the grid. You're going to try to learn a value function, which is expected discounted cumulative reward for each state. And through TD learning, you're going to learn the value function associated with each state. And given the value function, you can then learn a policy, and you go back and forth, as you know. So instead here, we're going to proceed in a hierarchical manner. we're going to consider primitive behavior that are up, down, left, and right. But these are always move up, always move down, always moves left, and so on. So once you get into one direction, you keep going along that direction. And then we're going to define different hierarchical level. For each state, we're going to ask at which level it is. Level zeros are states from which, if you follow the primitive behavior, you're going to get to the goal. So here, if you keep going left, you get to the goal. If you keep going right, you get to the goal. So all those states are level 0 states. Level 1 states are going to be states from which you can get to level 0 states, right? So if you're anywhere here, if you, again, use one of those primitive policy, in this case, go straight down, you're going to get to a state that's at level 0, those guys, right? And reverse here. And level 2 is going to be states from which, if you follow the primitive policy, you're going to get to level 1. Okay, so now, what's going to happen is that every state is going to be characterized by value functions that correspond to the different hierarchical levels. So if I have 6 different hierarchical levels, every state will have 6 value functions that have to do with asking, am I going to reach, if I follow the primitive policy, a state in a lower level of the hierarchy? And once we learn this, then we're going to have a policy gradient network that's going to learn to map this into a policy. So this is a big difference with regular TD. Regular TD, one state has one value function. Here, each state has a vector of values. In fact, for those of you familiar with this, they're known as generalized value functions, or GVFs. And the beauty of GVFs is they can be learned with just TD learning. You don't have to do anything kind of fancy. From a learning point of view, all of those guys are going to learn through TD learning. And this is just going to be learn the policy through policy gradients. And we're testing those networks in world that varies. So here, what's happening is we have a particular maze for a certain number of trials. And then after n trials, a new episode starts where the maze suddenly completely change. The goal is a different location and the configuration of the maze change. And we're going to ask, how well do we learn in such environment? We have multiple instances of the same kind of problem. And this is where the computational approach works really well and learn very quickly. After being exposed to a few of those mazes, then performance stabilizes to high level, much better than what you would get from policy gradient, Q learning, or extended Q learning. And the reason is because of this. Because learning the GVS here, which is maze specific, every time you get a new maze, you're going to learn, of course, what is the value of the different states, the different positions. That's super fast because our policy have no variance. I basically decide if I go straight up or straight down or straight right. So I have no variance. When I go from A to B, I always go in the same way. And that's a big difference with Q learning. Q learning will figure out all the different ways from go to A to B and try all of them. And that takes forever. Here, we go very, very fast. So in fact, you can show that it's like few shot learning for the GVS when you're in a new maze. This is what this is showing here. However, you still have to learn the mapping from the GFs onto the policy. And that's something that's, however, maze independent. Once you know your state of GVS, knowing the policy doesn't depend on the configuration of the maze, because it's the configuration of the maze is already captured by the GVS values. So once you've learned this mapping across a few mazes, it's going to generalize to all the mazes you're going to try ever after. So this is a bit slow. This requires to try a few mazes, but one that's learned is learned for good. And this has to be learned on every maze, but it's super fast because there is no variance. And that's why we get the things to work really well in this case, and why it beats all the others. All the others, basically, the problem is Q learning is that once you've learned one maze, you're basically starting from scratch when you're trying to learn the second maze, and you have to start from scratch again. So we got it to work on other problems. This is, I don't know if you're familiar with this, is a potion problems that DeepMind has designed to really push TD learning. So you have a potion, you have rocks, and you have potion to your disposal. You can apply potion to rock, it turns into another rock, and each rock is associated with a certain number of points. And you have to figure out how to get to the high value rock, the diamond at the end here for plus 15 points. And we also beat all the algorithms that we've seen on these kind of problems. We can do it on reaching tasks as well, where again, we get this approach to learn to reach for targets much faster than TD3, for instance. So I went a bit fast over this, but I also want to leave just a little bit of time for questions. But here, really, the idea is to see how a system can learn on its own without any extra supervision, how to break down a problem into a composition of much simpler behavior. Because again, I think my strong belief is this is definitely something that even rodents can do to a small extent. And then every time you multiply the size of the brain by a factor of 10, you get better and better at that. And it looks like by the time you multiply the size of the brain by a factor of 1,000, and you end up with 70 billion neurons, and apparently you start getting property-like language. And this is not unlike what we're seeing currently. I'm just going to quickly mention, I'm sure you guys are familiar with the latest release from Google called PaLM, which is like BERT and GPT-3 on more than steroids. I don't know, for me, first time I read it, it was like, this can't be serious. 540 billion parameters. The brain is 70 billion neurons, right? So we're entering like really absolutely crazy number of parameters. I don't know if you've tried it, but it looks completely stunning. They have a nice animation of what happens as you go from 8 billion to 540 billion parameters and the kind of property that you get. So it does look like size matter. It makes a big difference. And I think one of the challenges for us scientists is to understand really the size, what is the size that matters? So I would argue that the compositional network that exists in rodents are the ones that have just completely exploded in size to eventually lead to the kind of linguistic capabilities that we have. And on that note, thank you very much for your attention. And I think we have a few more minutes for questions.
Yeah, thanks very much for a super interesting talk. So indeed, we have time for a few more questions, a few minutes left.
I have one, if that's okay. So what do you think about the relationship between the fine-tuning in the language models that you did and grounding? So does that produce grounding of the language model to any degree? Or would it be possible to check whether the fine-tuned model has like better causal consistency in generating language afterwards if you ask it questions about the kind of things that the tasks are composed of?
So I'm not a linguist, and I'm not, I mean, I understand the concept of grounding to some extent, but I'm pretty sure I don't know the formal definition. But in a way, isn't grounding understanding, like, isn't part of grounding understanding how a set of words relate to action and to what you should be doing, right? I mean, I know that language is not just about action, but certainly part of it is. And certainly in early years and the early stage of evolution, it seems very likely that grounding language was about grounding it into action. And I feel like this is very much what this network is doing. Unlike many of the PaLM GPT-2 that I'm seeing out there that are trained just on predicting the next words, this thing here is trying to get language to understand how it's related to action. Mm-hmm. So yeah, the fine tuning in my view is a way to make sure that it's even better grounded in actions.
Yeah, but then this should be possible to check. I mean, a typical failure mode of these large language models is that they produce nonsense in a way that has like physical contradictions in it. So at least in relation to the kind of causal relationships that are present in these tasks, this should be reduced. Maybe it's not that easy to test, actually. I don't know.
No, I think you're putting your finger on exactly the kind of stuff that I really find fascinating. When I see the failure mode, it's pretty clear that's what's missing in those networks is like internal model of the situation they're in that allows them to really now generate much better prediction of what makes sense and what doesn't make sense. So I think it's partly done in those transformer network, but I think it would make a lot of sense to hook up those networks to way more complex network than the silly RNN that we had here that have the ability to build a model of what the situation is about. And I think that ability is what all animals have to some degree, right? And the language modules just plug on top of that. And I think they're going to avoid those bizarre generalization once those AI people manage to pair those networks in the right way.
Thank you.
And if anybody wants to do this, please come and join my lab. Right, or we'll leave soon.
We already had quite a few questions. Maybe there's like time for one more quick question if there's a general one left. We already had quite a few questions during the talk. No more general questions. Okay, fantastic. Well then, thanks very much again for a super interesting talk, and we can move on to the individual meetings. Thanks very much.